Okay, welcome to Note Set 2. We'll just do a quick introductory motivational speech here, talking about why linear algebra. Why do you have to study this? In the previous one I forgot to introduce myself. I'm Professor Mark Fowler, so I'll be creating these videos, and at least for the first summer offering of this, I'll be the instructor of record. So you'll also see my name down here at the bottom, along with another professor's name. Professor Zhang just taught this course on campus in spring of 2016, and so he did the bulk of the work in creating the notes. I helped out with that, and then I took what we created together, and I've edited them and modified them to some degree for this. But I do need to give him the bulk of the credit for creating the notes. So on each note set slide, you'll see my name up here saying that I'm the one doing the lecturing, and then you'll see both our names down here saying we are the ones who created the notes, and Professor Zhang did the bulk of the work. So linear algebra has been around for a very long time. Going back to before 1700, we'll revisit this slide towards the end of the course, to kind of see where we went. But so back before 1700s, there were some concepts similar to some things that we'll talk about. And then, these are just the main highlights, and you can see some famous names like, Leibniz, Laplace, you may have heard of Lagrange, you've certainly heard of Gauss, and Cauchy. Those are very famous names. Cayley, and Frobenius, maybe you haven't heard of, but they're big names in linear algebra. Anyway, the point is that back in 1955, a long time ago, from your perspective, still, more recent than 1700s, but still 1955 to you probably seems like a long time ago. That's when linear algebra first entered undergraduate education, and probably primarily in the math department. But within the last 20 or 30 years, it's become really fundamental to electrical and computer engineering undergraduate education, and some programs even had it in their curriculum long before that. But anyway, this just gives you a idea that this stuff has been developed over a long period of time by some of the greatest names in mathematics. So just some perspective on some examples of where these things might show up, without getting into all of the details. Linear algebra and matrices are at the heart of encryption, as well as at the heart of image processing. So every time you look at an image, it's really nothing more than a matrix of values, and when we process an image to do things to it, like change its color or remove some noise from it, de-blur it, things like that, those are all things that we can do as engineers, electrical and computer engineers, to process an image. We apply matrices to the array of values, and in power systems and other circuits. So these are all the symbols that power systems engineers use to, indicate, generators. So if you're taking your circuits course right now, at the same time, maybe you'll be introduced to these symbols. And we've got inductors and so forth. And so this big power system ends up being can be represented by a matrix. And then another application is in social networks on computers. Social networks can be characterized by matrices, and their performance can be predicted and analyzed by linear algebra methods. And those are just a few of the areas. So just to take a closer look at an image, So there's some very colorful image, and that image may have been created by this array. So array is another word that means the same thing as matrix. So here we have a 1920 by 1080 pixel array. We're obviously just showing a single part of it. And you can see here that we've got some red ones, we've got some blue ones, and we've got some green ones. That's the renowned RBG, red, or RGB, red, green, blue. So there's actually a sensor for each of those three colors, and those three colors make up the components that we can use to build any other color. And I find it interesting that this serves as an example of an array, but also that idea of having components that are used to build other things is also fundamental to the idea of linear algebra, as we'll see. And so this part at the bottom here is just showing that if this is our original image, it can be broken down into the red components, the green components, and the blue components. This is just showing where these pictures came from. One picture is actually made up of three different matrices, each matrix essentially holding an integer value in each of its locations. So we can represent different shades of red by giving a number typically between 0 and 255 or something like that, to give 256 different shades of red. Same thing for green and same thing for blue. Social network. So this is just showing all the different interconnections between different people or computers. And that network can be characterized through something called an adjacency matrix. And then the performance or the characteristics of that social network can be analyzed through linear algebra methods applied to the adjacency matrix. And then here we have the power system that we showed. This is the circuit diagram showing inductors for the transmission lines and current sources for the generators and so forth. We can write a matrix that describes that system. So this matrix here describes all the components in the network, and where those values show up in this matrix characterize the interconnections. So these components are described by complex numbers called admittances, which are related to impedances and resistances, which you'll be learning about in your circuits class. And it's this admittance matrix that connects the voltage vectors. So this is a vector of 4 different voltages, so voltages at 4 different places. You can see them marked here. So I can't quite read it, but we've got V1, V2, V3, and V4, I think is how those are labeled. So it links those voltages to the currents, and we just have I3 and I4. So I'm not quite sure where those are indicated on this diagram because it's a little blurry. But the big idea is that an admittance matrix connects voltages to currents. So as engineers, we use this setup to, if we know what the admittance matrix is and we know what the currents we want or have, we can solve for what the voltages will be. And this problem will take up a tremendous amount of our attention in this course, solving a matrix equation like this. And it turns out, as we'll see, to just be a convenient, compact way of representing a set of linear equations, simultaneous linear equations. So, this course is being offered through the ECE department, so I'm assuming that you're an ECE student, although we might have some who are taking it outside of that for whatever reason. But we're going to focus on ECE applications, and this is just a short list of some of the things within the ECE field that where linear algebra is extremely important. And so some of these phrases will mean nothing to you perhaps at this point, but some might mean something, and most of them are fairly descriptive, so you can get some kind of idea. So, circuit analysis, obviously, that's pretty bread and butter to ECE. You've got a circuit, you need to analyze how it's going to behave, and linear algebra will do that. And as I said, if you're taking a circuits class already or at the same time as this, you will be learning about how when you write these equations that describe the circuit, they can be put into matrix form and solved. Then we have a field known as control theory. So, very simple, common thing that you know about is, like the furnace and thermostat in your house. The thermostat is sensing the temperature of the room and controlling when the furnace comes on and turns off. But you could also have more complicated things like cruise control on your car, which monitors the speed you're going at and then automatically controls the inputs to your engine to maintain a constant speed regardless of the terrain over which you're driving. And then a more complicated thing would be autopilot. Now these things are kind of automatic, but we also use control theory to be an adjunct to human control. So when the pilot is actually moving the stick to make an airplane do a certain thing, there is a control system that is monitoring what the airplane is doing and then modifying what the pilot has done in order to make the airplane I shouldn't say modifying, combining its own signal with the signal from the pilot to make the aircraft respond in the way that the pilot is anticipating. Then we have an area known as signal processing. So signal processing is all around you. So whenever you're sending signals over your phone, or you're using some sensor to measure something, or when you are say in a battlefield scenario, you're trying to detect the presence of enemy planes or estimate how fast they're going or how far away they are, all sorts of things like that. Network theory, long ago that really was synonymous with circuit analysis, but here I believe it's indicating an application to like computer networks. How do we understand the performance of computer networks and how do we design them so that they are very efficient and fast? So linear algebra applies in there. Music compression, video compression, all those use ideas from linear algebra. So when you're converting your video into an MP4, just like I am doing so with this video that I'm recording right now, it'll get converted into an MP4 file. That's video compression so that it will be able to be stored efficiently on my computer and put up on YouTube or wherever, Blackboard in this case. So video compression draws highly from the concepts of linear algebra. And then not just ECE, but all engineering problems basically boil down to optimization problems. So I give one simple scenario here. If you're an electrical engineer and you're trying to lay out the parts on a chip, the components on an integrated circuit chip, that would lead to an optimization problem that could be formulated in terms of linear algebra and then solved. And then image processing. So, you might have a camera that is taking a picture of, somebody's license plate for, maybe for terrorism aspects. Due to the motion of the car, the license plate picture is blurry. You can do processing of that image to remove some of the blur. And again, that's all highly dependent on ideas from linear algebra. And then the big one, etc. There's lots more that we already know, and there's lots more that we don't necessarily know. So things in the future, technologies that will develop, ideas that will develop either within these areas or outside of them, will take advantage to a large part of linear algebra. So I cannot overemphasize how important this topic is to what engineers do all the time. So one point I want to make is that even though all the problems in these areas look different or may sound different, they actually all boil down to solving the same kinds of problems. And that's the beautiful unifying thing about mathematics in general and linear algebra in particular. It really has this unifying aspect to it. So before I came to be a professor at Binghamton, I worked for 8 years at Lockheed Martin, and I worked on a lot of different projects, and I was kind of the algorithm expert there, and so people would bring problems to me that they didn't know how to solve. And I can't tell you how many times people brought me problems that they thought were different from things that they brought me in the past, but were really pretty much the same problem, just physically looking different, but under the hood, the mathematics was the same. So, I must have seemed like I really knew an awful lot of different things. In reality, I was just applying the same kind of tools over and over and over again. So that's hopefully conveying to you that this topic is a real lifesaver sometimes when you're working out in the field. And so for all engineers, like I said, linear algebra is this unifying, powerful tool that allows you to, kind of have this unified approach to many different problems. I can't think of a more critical tool that I have in my toolbox. So let's just take a quick look at some things. Now, you may not have the background yet to understand all of this, but that's okay. I'm just trying to show you how an engineer might go about setting up a problem and then using linear algebra to solve it. And again, even the linear algebra part of this you don't necessarily know yet, but I would encourage you to come back later after you've gone through some of the course, take a look at this set of notes, and you'll go, now I'm seeing it a little bit clearer. So this first circuit, very easy to solve. We don't really need linear algebra for that. We've got two resistors here that are in series. So, from your circuits class, we can just add those two things together to get the equivalent resistance. And we have 15 volts applied across those 2 points. So that's 15 volts applied across 15 kiloohms. So we can very easily solve, that should be 1 milliamp of current flowing in that circuit. So that's easy. No linear algebra needed, but algebra definitely was needed. Linear algebra extends that idea and makes it a much more powerful tool. So now we've got a circuit here. We've got two different voltage sources, so it's like having two different batteries. We've got three resistors connected in this kind of T shape. Engineers say that we basically have two loops. So this is a two-loop circuit. And, how do we solve this? Well, I'm going to take you through that. And again, I'm not expecting that you don't have to know how to do this. You either have or will learn it in your circuits class. So our job is, given these voltages of these two voltage sources, and given these three resistors and their connection this way, solve for the currents that are indicated here. So current I1 flows here, and actually I1 flows everywhere, from here around over to here. I2 flows everywhere along that leg, and I3 flows everywhere along here. So, if you're not used to circuits yet, think about the flow of water. These are like water flowing in pipes. So we would like to solve for these things. And so we can write these equations down based upon two rules, both by a guy named Kirchhoff. So we have Kirchhoff's voltage law, or KVL, and Kirchhoff's current law, or KCL. And so we write those down. It's not important right now if you know how to do that or not, but notice that we get three equations, three linear equations, and we've got a bunch of variables, and some of which we know. So we know V1, we know V2, but we don't know VR1, which is the voltage across R1. We don't know VR2, which is the voltage across R2, and so on. And then we have one equation here, which we know none of them. I2, I1, I3, we don't know any of those things. But yet we can still write that down as a fundamental equation. And then we can apply Ohm's law. So if we apply Ohm's law to the first two equations, we get something that looks like this. And then we can plug in the specific values that we have. And we end up with two equations in two unknowns. Now, maybe you know how to solve these easily by hand. It's not terribly difficult. You probably learned that in your high school days, or maybe at some point in college you revisited that. But you can easily solve these. But we could transform this set of equations into a matrix vector form. So we've got a matrix here, and you'll notice that this matrix here holds the coefficients of the equations in the right order. So we've got I1 and I3 here as our unknowns. And notice that if we can find I1 and I3, we know I2 already. So really we just need to know I1 and I3 to find that. And then over here, the 15 and the minus 10, they came from the voltage sources, so those are known. And the 15, 5, minus 5, and 10 came from the resistances that we have here. So this matrix vector equation is something that we could solve, and we'll talk about that in this class. But for this circuit, do you need to go to this matrix form? No. Like I said, you can easily solve it by by the simple methods you learned in high school. But it's pointing out that we could solve this using linear algebra methods. And when we get to extremely large circuits, like a huge power system or a very complicated electronic circuit, solving these things numerically, we don't have to actually sit down and write out the equations and solve them. We can put them into a computer and have it solve them for us. So it makes it very easy to solve for very large circuits. Now, I know you might at that point be saying, well, if a computer can do this, why do I need to even know how to do it? Well, someday you may be the person in charge of developing the software to solve these things. So you better understand how it works. And the more you understand about how your tools really work, the better you will be at using those tools. So to blindly use computer programs that you don't have a clue what the basis of their operation is, bad scenario to be in. So you need to know how this works. And in a course like this, you'll apply these ideas to small scenarios to gain an understanding of how these things work and get a feeling for when they will work well and when they won't work well. Now here's another problem that you're probably very, very familiar with, and that's web page ranking. And I point out that really this is a computer science problem, really, but some computer engineers are involved in this type of stuff. So how do we rank the websites on the internet? So if we're trying to search for all the websites that might be of interest to somebody based upon some key terms that someone types in, well, there's millions and millions of websites that might have those keywords in them, but we'd like to find the most relevant ones. And so that turns out to be something that is done every day. When you go to Google and you type in, say, for example, linear algebra, you'll get a list, and that list will go on and on and on and on, but you can be pretty sure that, well, yeah, see here we have almost 9 million results, and they list 5 of them here at the top, and yeah, Wikipedia right there at the top. Now, you could say, well, they just know that Wikipedia is a good site and they put that at the top. Well, that's not really how it works. And you'll also notice that this was done in less than a quarter of a second. So that's pretty fast. So how do we rank this? Well, it turns out to actually be a math problem. So the math problem in words is, according to how the mathematicians say it, rank centrality of all nodes in a graph. So nodes, graph, centrality, these are terms that we might not know. We kind of know what a graph is, but maybe not the way it's being used here. But that's how a mathematician would pose this problem. And back in 1996, there were two grad students, Larry Page and Sergey Brin. So as grad students, they figured this out. They found the linkage between a problem that they were concerned with, which was internet page ranking, and this math problem that was in the world of linear algebra and some associated nearby areas of math. And this node centrality ranking problem boiled down to finding a matrix and then computing these things called eigenvalues and eigenvectors. Now, you may have seen those words before. We will cover those towards the end of the course. But for right now, you just need to know that those are some cool things that come out of linear algebra. And they are tremendously useful for a lot of things, not just linking or not just finding the node centrality ranking of some graph. So we will study that later. And as I said, eigenvalues and eigenvectors pop up all over the place in engineering problems. And so they used that idea to provide a real-world solution to this internet page ranking problem, and they wrote some software to do that, and they called it PageRank. And then 2 years later, they founded an internet search company called Google, of course. And now they're worth lots of money. And so largely because they were able to look at a real-world problem and recognize the underlying math problem that would allow them to efficiently solve this. So math can actually lead to great wealth if you know how to use it. There's no guarantee that will happen, but it can. So linear algebra, how do we use this as a unifying tool? Well, we just saw the guys who founded Google using math to solve one particular problem, but they did it by mapping a real-world problem into a math problem. And that shows the power of using these universal unifying tools. So we start down here with some real-world problem, and we are looking for the solution to that real-world problem, and we might not know how to do that. But fortunately, there's the parallel math world, and we may be able to take this real-world problem described in physical terms and write it out as some math problem, and it might actually turn out to be a well-known math problem. It might not be well-known. You might have to then figure out how to solve it mathematically. But a lot of times it's well-known, or at least reasonably well-known, and then you immediately have a well-known math solution which just kind of drops out of nowhere for you. And then you go back you take that math solution, map it back to the real world, and at least in the case of the founders of Google, you get some money for that. But that's what engineering is actually all about. And that's why you're required to study math. So, I know a lot of students say, I don't want to do the math. I just want to build cool things and design cool things. Well, sometimes you can just do that by intuition, but more often than not, it helps to solve the really challenging design problems with the help of knowing some math. And again, harking back to something I said a little bit ago, well, if my computers can solve these things for me, why do I need to know how to do the math? Well, sometimes your computer may not give you an answer that is reliable for some unknown reason. And if you know nothing about how the real world problem maps to the math problem, you may end up applying that computer solution in a way that's inappropriate or to a problem that's inappropriate. So the more you know the underlying math, the better you can apply that tool. And I've been telling you that this is just a critical tool that you have available to you in your toolbox. And so I'm showing here linear algebra up at the top, and some things that are either based upon linear algebra or applied with or through linear algebra or are closely related to it. So we've got control theory and graph theory, machine learning, any kind of optimization, which is basically everything that engineers do. This machine learning is becoming more and more useful today. That's all based upon ideas out of linear algebra. And we've got power systems and robotics and network analysis and this thing that we'll talk about later called the singular value decomposition, and linear programming, which is a technique used for solving huge optimization problems. So really, I guarantee you linear algebra is at the heart of a lot of things that are making your world exciting, interesting, and worthwhile. So the problem that we're going to be looking at, we've already seen in this set of notes. So it's just solving this matrix equation. And it won't always just be a 2x2 matrix and 2-element vectors. We'll be interested in solving it with any number of elements. But typically, we will talk about the matrix being known. So that'll come from the physical parameters of the problem, in this case, the resistances of the circuit. And then there will be some known vector over on the right side. And in this case, that came from the known voltage sources. And then the link will be the matrix of resistances times the vector of currents, which are unknown, gives the known voltages. And so what we need to do is crack this open. So right now the currents are mixed together with the matrix. And so what we need to do is somehow swing this over to the other side. So, in the case of a simple algebraic equation, we might have like 5i is equal to 15. That's easy to solve. Divide both sides by 5 and you get I is equal to 3. So that's the easy way to do it. So we need some way of, dividing both sides, I should say, quote unquote, dividing both sides by this matrix. And that will lead us to this idea of an inverse matrix. And there will be some other ways that we'll use to solve this set of equations. But it's really much more than just solving these. If all we were interested in is just having a tool that allows us to rip through this and solve the problem, this course wouldn't be terribly interesting. But to see why it works and when it can't work and what makes it, maybe close to not working, those are the things that we're interested in. And again, I'm urging you, I'm pleading with you to not treat this course as I just need to know some stupid little set of steps to allow me to solve this kind of problem, and I don't want to know anything more than that. That may get you an okay grade in this class, but it will lead you down a path of not really becoming the best engineer that you could be. And, really to stay employed today, to find work and stay employed as engineers, you really want to strive to be the best possible engineer that you can be. Then you will have a long and prosperous career, even though there may be some economic downturns. You'll have a better chance at remaining a viable contributor. So we will rewrite this matrix that we're showing, this matrix equation that we show here in particulars. We'll write it in this general form. A will be our symbol for the matrix. X will be the unknown vector that we're trying to find, and B over on the other side will be the known vector that sits over there. And right now we haven't explained to you what it means to multiply a matrix times a vector, so we will be explaining that in some of the upcoming node sets. You may have seen that already, but if you haven't, don't worry about it. So the question is, how do we solve AX is equal to B? And so we would like to be able to do this numerically. So that's the just tell me how to do it. We'd also like to be able to do it analytically. And by that we mean more than just, ending up with a final equation. We want to know, why that works. And we want to know what are the conditions under which it might start to not work so well. And that leads to this question: what are the issues that arise for numerical solution? So we will find that there are cases where you write down these equations and there will not be a solution. And even though we don't go into this next idea very deeply, there are issues where technically, theoretically, the equation is solvable, but it's so close to being unsolvable that a small round-off error can cause problems. So if you understand the material in this course, you'll understand why that might happen and how the fix actually works. So when can we solve the problem? And then the last thing, how can we visualize all these concepts and issues involved? So I often get students coming to me and saying, I want to be an inventor. I want to invent things. But they're often, it's funny, often students who say those things they're so eager, they don't really want to spend the time learning the fundamentals and the concepts and the issues. They just want to go off and do something. Well, learning how to visualize these ideas and being able to think through in your head how all this machinery works, those are the things that lead you to innovation. So if you want to be the person who's out there innovating, coming up with new ideas, forget about focusing on, I just need to solve this stupid problem that I have, and think more about what are the concepts? How do I visualize these concepts? What are the issues? Why does it work this way? What might make it not work? What might transform this non-solvable equation into something that is solvable? And so that's where we're trying to go. And then towards the end of the course, we'll talk about a related problem that shows up in scenarios like video compression, audio compression, image processing, like that problem I talked about, deblurring a photo of a license plate. In those scenarios, you have an X. So X might be the thing that you have. So I know I said images are matrices, but we could remap a matrix into a vector. So we take that license plate picture and we reorient it into a big vector. And then we want to pick a matrix A that will operate on it and convert it into some new B. So it's not so much that we're trying to solve for B, we're trying to transform X into some new unknown thing. And the goal is that when we end up with this new thing, after we've done this processing, we get this new B. If it were if X were a kind of a vectorized image, we could unvectorize B into a new image, and it would be a deblurred version of the original license plate. Now, we're not going to get into the details of these cool things in this course, but we are going to cover the meat, the fundamentals that are underneath all that, so that then when you go on to the next courses, you'll be learning some of those things in the context of linear algebra. So in this context, we think of A, the matrix, mapping vector X into some new vector. We think of it as an operator. A is a mathematical operator that operates on vector X to give us some new vector B. And often we get to choose that A. So this is where a lot of cleverness and ingenuity comes in. And if you understand the concepts, rather than just, I need some always workable A that will do this for me. If you understand the concepts for a given problem, you can sit down and figure out, I got this X, it's got these problems, I want to fix those. What A do I need to use? So we need to try to understand when we apply an A matrix to a vector x, what does it do? So that we can try to uncover some interesting hidden structure in x, or we can, pick the matrix A to transform it over into a new, better version of the original x. So when can we map x into a desired B? And then how do we do this numerically, but in an efficient way so that our computers can do it quickly? And lastly, again, all about visualization. How do we visualize all of this? Then you can be the innovator. So where do we go first? Well, we're going to start with solving this equation where A is known, X is unknown, and B is known, and we're trying to solve for X. That's what we're going to cover. So, but to get there, we need to talk about how do matrices and vectors work together. So what are vectors? How do they behave arithmetically? How do they behave geometrically? So we'll talk about the geometry of spaces of vectors. It'll be called vector space. And then how do we combine vectors into other vectors? And this will be a process called linear combinations. And then we'll define matrices, and we'll talk about how to multiply a matrix times a vector, and how to multiply one matrix times another matrix, and so on. And let me back up here. And so that's what we're going to be doing for this course, and hopefully you'll find it very interesting. But we'll start here with the simple problem, and we'll go all the way to the end. And along the way, we'll try to point out how these things apply to very specific ECE problems.